Okay, here is a walkthrough through the 2006 Physics B question that I'm just going to call the spring Atwood machine problem. And this is a pretty neat problem here because essentially the block and the pulley, the two block system and the pulley is like an Atwood machine. Let's see. And here. Oh, come on. Okay. All right. So let's go ahead and read this. So an ideal spring of unstretched length is 0.2 meters, is placed horizontally on a frictionless table as shown above. One end of the spring is fixed and the other end is attached to a block of mass, which we're going to use capital M, and it has a mass of 8 kilograms. The 8 kilogram block is also attached to a massless string that passes over a small frictionless pulley. A block of mass little m, which is 4 kilograms, hangs from the other end of the string. When this spring and block system is in equilibrium, the length of the spring is 0.25 meters. And the 4 kilogram block is 0.7 meters above the floor. So there's a lot of important information that we were given. So we were given the initial length of the spring to be 0.2 meters, and then the final length to be 0.25. So that means our change, so how much the spring is stretched at this point, is 0.5 meters. That will definitely come up. Okay, we're given the height, 0.7, and the other important thing is that it says it's an equilibrium. So when we start looking at forces, everything is going to be balanced from A through C. Okay, now the reason why this is an excellent review problem to do is because this does test us, this does review us on forces, kinematics, and even the stuff that we just did with oscillations. Okay, so this is just going to be free body diagrams. Hope you don't mind if they're different colors than they were in the previous page. Okay, so this is for M, which is the 8 kilogram. This is little m, which is the 4 kilogram. Okay, so the forces here, very simply, we have tension from the string. We have spring force in the opposite direction. We have weight. And then we have the normal force from the track. Okay, very easy. Try to make those arrows the same size so you can show that you know that the net force is 0. That's what they're looking for here. Okay, for the one that's hanging, there's only 2 forces. We only have tension, and then we have its weight, little m and g. Alright, that's A. Very, very easy. Should be easy points. Moving on to B, we want to find the tension. Okay. So, keep in mind this is when it is in equilibrium. So we want to go back and we want to look at that the hanging mass here. Okay, if this is tension and this is mg and they're in equilibrium, that means that tension is going to equal mg. Okay, remember, for these problems, to make it easier, I'm going to use g as 10. Okay, it's just much, much faster. Alright, and it's accepted on the EP exam. So this is just 4 times 10, which gives us a nice 40 newtons. So this is B. And then C asks us about the spring constant, so we're looking for K. Well, if we look at the 8 kilogram block, let's just look at the forces in the X. Remember, we had tension, and then we had the spring force to the left. Okay, so if we are in equilibrium, which we are, then that means that the spring force is going to equal the tension force. So that means the spring force is also 40 newtons. Now, of course, it's to the left. Okay. So if we look at our spring force minus kx, so minus 40. If you want to be, it's going to cancel out anyway. And then our change in x was 0.05 meters. We found that on the very first page. Okay, so these are going to go away. So then K is 40 newtons divided by 0.05 meters. You get 800 newton meters. Wonderful. Okay, now D, E, and F. The string is cut. Okay, and it tells us it is cut at point P. Let's go back to our diagram. So it's cut right here where I tried to draw. Alright, right at point P. So notice that point P is to the right of our block. Okay, so how is this going to affect the situation? Okay, well, let's identify it for both. Okay, so before we even start solving D, E, and F, so what's going to happen to the 8 kilogram block? Well, remember the spring is acting on it. So the spring is going to cause this one to oscillate. It's going to cause capital M to oscillate. So simple harmonic motion. I hope I spelled this right. Oscillate. I know I did not. I don't think so, but it's okay. And then the little m, our 4 kilogram mass. Well, look, if this is cut, this is just going to fall. It's going to be in free fall because there's no tension acting on it anymore. So that's the important thing. So when you cut the string, there's no more tension. So that means it's just going to be in free fall towards the ground. Okay? That's how the situation is being changed. Okay, so now let's look at the time taken for that 4 kilogram block to hit the ground. So this goes back to kinematics here. And so what you want to look at is, if you're looking for time, this is definitely the equation to use here. Plus 1/2 a time squared. Okay, so obviously a here is negative 9.8. So that plus sign is definitely going to go away. Okay, and we're looking for t squared. Now this is 0.7, and this is 0 because it's going to hit the ground. And this is 0. Okay, so let's clean this up. All right. So we get minus 0.7 meters is equal to, oh, and I forgot. I'm just going to use 10 here. I mean, it is minus 9.9, but let's make it easier. Okay, so 10 divided by 2 is 5. And this is t squared. Okay. Alright, so then t is going to equal, right, so this is going to go away. So we're going to get a positive value under our radical there is going to equal 0.7 divided by 5. And that comes out to be 0.37 seconds if you're using 10. Okay, before, underneath the square root, if you want to know that, is just going to be the square root of 0.14. Okay, so there's our time. It's just free fall. Okay, so this last part is relevant to what we have been studying in the last week. Calculate the frequency for oscillation. Okay, so this equation is on the AP sheet, so that's wonderful. You don't have to memorize it. Okay, remember a higher K value is going to increase the frequency. Okay, so we know K, we know M. This should be a simple plug and chug. Alright, so let's plug these in. And I know we love to use our calculators, but sometimes, and this is capital M here, this is the 8 kilogram mass. Sometimes, you know, you can simplify things with your mental math, okay? Because look how this simplifies. Square root of 100, which you should all know, to be 10. So then you have 10 over 2 pi, or 5 over pi. Right? That simplifies a ton. That right there will reduce the error of you making a mistake in the calculator. And that comes out to be 1.59 hertz. That's what I got. 1.59 hertz. And then the last one says, what is the Vmax? So of the 8 kilogram block, that's what it's asking for. So the one in oscillation. So this is the equation that we just talked about. The Vmax is equal to 2 pi f a, and the amplitude, so we know this to be 1.59, the amplitude is 0.05. That's how much it is stretched. Okay. Alright, because remember the equilibrium position is considered 0. Alright, and you know, this looks like it's going to be an ugly number, but it cleans up to be exactly 0.5 meters per second. Okay. Alright, so this equation is not on the AP sheet. Could be useful to know. Okay, there are going to be some equations that are, you know, just going to be useful to kind of remember. You know, you can make this easier to remember if you remember that this relates to circular motion. Okay, so I showed that in another video. And so remember that linear velocity for a circular object, okay, remember is, I mean, if you look at the distance over time, the distance around a circle is 2 pi, and then r, okay, and r here is the amplitude. Okay, so if you think about that, that's 2 pi a over t, and then frequency is equal to 1 over t. Okay, so if you remember that concept, then that really reduces the memorization needed. Okay, hope this helped. Thanks.